Hello everyone. Welcome back to my course Aerospace Engineering, Rocket Science Basics. In this video, we will talk about rocket attitude control, axes, rotations, and control systems. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comments section or reach out to me via the email provided in my profile. Rocket rotations. Since rockets operate in a three-dimensional world, it is essential to control their attitude or orientation along all three spatial dimensions. During flight, a rocket can rotate about its center of gravity, which is the average location of the rocket's mass. To describe this rotation, engineers define a three-dimensional coordinate system with its origin at the center of gravity. Each axis in this system is perpendicular to the other two, allowing precise measurement of how the rocket rotates along each axis. The attitude of the rocket is then defined by the amount of rotation along these principal axes. Most rockets are designed to be symmetric along a line extending from the tip of the nose to the center of the nozzle exit. This line is called the roll axis, and rotation about it is known as rolling motion. Because the rocket is symmetric around this axis, this configuration is referred to as axisymmetric. Importantly, the center of gravity of the rocket lies along the roll axis. To define the other two principal axes, we identify a distinct feature of the rocket, such as the placement of a fin or a window. The yaw axis is then defined as perpendicular to the roll axis and also passing through the center of gravity. When a rocket rotates about the yaw axis, the nose of the rocket moves side to side. This type of rotation is called a yaw motion. The pitch axis is perpendicular to both the roll and yaw axis and also passes through the center of gravity. Rotation about this axis causes the nose of the rocket to move up or down, and this motion is referred to as pitch motion. To visualize these axes, imagine a line drawn along a fin at the top of the rocket. This line lies in the plane formed by the roll and yaw axis and helps define the yaw direction. Rockets can be maneuvered using several techniques that generate rotational forces along the principal axis. During flight, the fins of the rocket interact with the air to produce aerodynamic forces. These forces act at a point, the center of pressure, which is located some distance from the rocket's center of gravity. The offset between the center of pressure and center of gravity produces torques, also known as moments, which cause the rocket to rotate. In most full-scale rockets, pitch and yaw motions are achieved by gimballing the exhaust nozzle, which means rotating the nozzle slightly so that the thrust vector is no longer aligned with the roll axis. When the thrust is not aligned with the roll axis, it creates a torque about the center of gravity, effectively turning the rocket in the desired direction. Examples of controls. Every full-scale rocket is built around four major components: the structural system, the payload system, the guidance system, and the propulsion system. The structural system, or frame, provides the strength and rigidity needed to withstand forces during launch and flight. The payload system carries the mission-specific equipment or cargo, such as satellites, scientific instruments, or even humans. The propulsion system generates the thrust required to lift the rocket off the ground and propel it through the atmosphere and into space. The guidance system is a highly sophisticated combination of sensors, onboard computers, radars, and communication equipment. It has two critical roles during launch. First, it provides stability, ensuring the rocket maintains the desired orientation. And second, it controls the rocket during maneuvers, making real-time adjustments to achieve the target trajectory. Rockets are controlled using several different methods. The motion of any object in flight is a combination of translation, which is the movement of the center of gravity, and rotation, which occurs about the center of gravity, also called the center of mass. All rocket control methods work by producing a torque about the rocket's center of gravity, causing it to rotate. By understanding the forces acting on the rocket and the resulting motion, engineers can program the guidance system to achieve complex objectives, such as intercepting a target or entering a precise orbit around the Earth. Movable fins. Early rockets, as well as modern air-to-air missiles, often use movable fins at the rear of the rocket for control. Adjusting these fins changes the aerodynamic forces acting on the rocket. Since the aerodynamic forces act through the center of pressure, which is usually not aligned with the center of gravity, this creates a torque about the center of gravity. This torque rotates the rocket to change its direction. For example, if a fin is deflected to the right, the resulting aerodynamic force will push the nose of the rocket to the right. This simple mechanical method was widely used before more advanced guidance technologies were developed. Gimbaled nozzle control. Most modern rockets control their attitude by gimballing the nozzle of the engine. In this system, the exhaust nozzle can be swiveled from side to side, which changes the direction of the thrust relative to the rocket's center of gravity. This produces a controlled torque that rotates the rocket. For instance, if the nozzle is pivoted to the right, the thrust vector shifts, causing the nose of the rocket to move to the right. Gimbaled thrust systems are highly effective and are the primary method used in modern rockets due to their precision and reliability. Vernier rockets. Some older rockets, such as the Atlas missile, used small auxiliary engines at the base of the main rocket to generate control torque. These small engines, known as vernier rockets, fired independently to rotate the rocket in the desired direction. While effective, vernier rockets added extra weight due to additional fuel and plumbing, which made them less efficient. As a result, this method has largely been replaced by gimbaled nozzles in modern rockets. Thrust vanes. Early rockets, like the V2 and Redstone, sometimes used thrust vanes placed directly in the exhaust stream of the main engine. By deflecting the exhaust flow, these vanes created a torque that rotated the rocket. For example, if a thrust vane is deflected to the right, the exhaust stream is redirected, and the nose of the rocket moves to the right. While ingenious for its time, this method is less efficient than gimbaled nozzles because it partially obstructs the exhaust flow, reducing overall thrust. Stability of a model rocket. During the flight of a model rocket, small disturbances such as gusts of wind or slight variations in thrust can cause the rocket to wobble or change its orientation, also known as its attitude in flight. Like any object in motion, a model rocket rotates about its center of gravity, CG, which is the point where the rocket's mass is balanced. This rotation causes the rocket's axis to tilt at an angle, which we denote as alpha, relative to the flight path. Whenever the rocket's axis is inclined, lift forces are generated by the rocket body and fins, while aerodynamic drag remains relatively constant for small inclinations. Both lift and drag act through the center of pressure, CP, of the rocket, which is typically located behind the CG. The relationship between the CG and CP is critical in determining the rocket's stability. Consider three cases where the rocket is intended to fly straight upward. In the center case, the rocket is undisturbed and its axis is aligned perfectly with the flight path. Here, the drag acts along the axis of the rocket and no lift is generated. On the left, a powered rocket has its nose slightly perturbed to the right. This inclination generates a lift force directed to the right, which acts to restore the rocket to its original flight path. On the right, a coasting rocket has its nose perturbed to the left. In this case, the lift force is directed to the left, again pushing the rocket back toward the intended path. For the powered rocket, both lift and drag produce counterclockwise torques about the CG. This causes the tail to swing to the right while the nose moves left. For the coasting rocket, the forces produce clockwise torques, making the tail swing left and the nose move right. In both cases, the combination of lift and drag acts as a restoring force, bringing the rocket back toward its intended flight direction. The presence of a restoring force depends on the relative positions of the center of gravity and the center of pressure. For a stable model rocket, the CP must be below the CG. This ensures that any small displacement of the nose generates torques that restore the rocket to its original orientation. If the CP is located above the CG, the lift and drag forces still act in the same direction, but the resulting torques are reversed. In this scenario, small disturbances cause the nose displacement to increase rather than decrease, creating a destabilizing force. You can perform a simple test to determine the stability of a model rocket. Tie a string around the body tube at the location of the center of gravity. Be sure the engine and parachute are installed. Hold the free end of the string and swing the rocket in a circle around you. Observe the orientation of the nose. If the nose points in the direction of rotation, the rocket is stable and the CP is below the CG. If the tail points in the direction of rotation, the rocket is unstable. To increase stability, you can either lower the center of pressure by increasing the fin area or raise the center of gravity by adding weight to the nose. Proper adjustment of these two parameters ensures that the rocket will remain stable during flight. Stability and control systems in rockets. Building a powerful and efficient rocket engine is only one part of creating a successful rocket. Equally important is ensuring that the rocket is stable in flight. A stable rocket flies smoothly along a uniform trajectory, maintaining the path intended by its designers. In contrast, an unstable rocket moves erratically, sometimes tumbling, changing direction unpredictably, or even turning upside down. Such rockets are extremely dangerous because their path cannot be predicted, and in extreme cases, they could return directly toward the launch pad. Achieving stability in a rocket requires some form of control system. These control systems can be either active or passive, depending on how they manage the rocket's orientation. Understanding these systems begins with understanding the fundamental factors that make a rocket stable or unstable. All objects, regardless of size, mass, or shape, have a point called the center of mass, cm. The center of mass is the exact location where all of the object's mass is perfectly balanced. A simple way to visualize this is with a ruler. If the ruler is made of uniform material, it will balance perfectly on a finger at its midpoint. However, if one end of the ruler is made heavier, for example by driving a nail into it, the center of mass shifts toward the heavier end. In rockets, the center of mass is crucial because it is the point around which the rocket rotates or tumbles when unstable. Any object in flight exhibits some form of rotation. A thrown stick tumbles end over end, a thrown ball spins in the air, and a frisbee will only fly accurately if it is given a deliberate spin. If the frisbee is thrown without spin, it wobbles and veers off course. Similarly, a rocket requires stability to ensure it follows the planned trajectory. In flight, rotation occurs around three principal axes: roll, pitch, and yaw. These axes intersect at the center of mass. For rockets, the pitch and yaw axes are the most critical because rotation about these axes can cause the rocket to deviate from its intended path. The roll axis, on the other hand, has the least effect on the trajectory. In fact, a rolling motion along the roll axis can enhance stability, much like a football that is thrown with a proper spiral. The spinning motion helps the football maintain a straight, predictable flight. While a poorly thrown football might still reach its target despite tumbling, a rocket cannot rely on this chance. Unlike a football, which only receives energy at the moment of the throw, a rocket continues to produce thrust while in flight. This means that any unstable motions along the pitch or yaw axis can quickly compound, causing the rocket to leave its planned course. To prevent this, a control system is essential to minimize or correct these unstable motions and keep the rocket on track. The center of pressure and its role in rocket flight. In addition to the center of mass, rockets have another critical point that affects their flight: the center of pressure. The center of pressure only exists when air is flowing past the rocket, creating forces on its surface that can cause the rocket to rotate around one or more of its three axes. A simple analogy to understand the center of pressure is a weather vane. A weather vane is an arrow-like device mounted on a rooftop to indicate wind direction. The arrow is attached to a vertical rod, which acts as a pivot point, and the arrow is balanced so that its center of mass is at this pivot. When the wind blows, the arrow turns, and the head of the arrow points into the wind while the tail points downwind. The reason the weather vane aligns this way is that the tail has a much larger surface area than the head. As the air flows past, it exerts a greater force on the tail than on the head, pushing the tail away from the wind. Somewhere along the arrow is a point where the forces on either side are balanced. This is the center of pressure. Importantly, the center of pressure is not at the same location as the center of mass. If the center of pressure and center of mass were at the same spot, the wind would not favor either end of the arrow, and the arrow would fail to point into the wind. On a weather vane, the center of pressure is located between the center of mass and the tail, giving the tail more influence over the arrow's motion. For rockets, it is extremely important that the center of pressure be located toward the tail, while the center of mass is located toward the nose. If the center of pressure and center of mass are too close together, the rocket becomes unstable, as small disturbances can cause it to rotate uncontrollably around the center of mass along the pitch and yaw axes. This creates a dangerous situation because the rocket can deviate unpredictably from its intended flight path. When the center of pressure is correctly positioned near the tail, the aerodynamic forces produce restoring torques that naturally bring the rocket back to its intended flight direction. This alignment is essential for maintaining stable flight, ensuring that the rocket follows a smooth, predictable trajectory rather than wobbling or tumbling. Rocket control systems. The purpose of control systems in rockets is twofold: to keep the rocket stable in flight and to steer it along a desired trajectory. Small rockets often require only stabilizing control systems, which keep the rocket flying straight and prevent it from tumbling. Larger rockets, such as those used to launch satellites into orbit, need more sophisticated systems that not only stabilize the rocket, but also allow it to change course while in flight. Rocket controls can be divided into two categories: passive and active. Passive controls are fixed components on the rocket's exterior that provide stability simply by their presence. Active controls, on the other hand, can be adjusted or moved during flight to stabilize and steer the rocket dynamically. One of the earliest examples of passive rocket control comes from the Chinese fire arrow. These were simple rockets mounted on the ends of sticks. The stick functioned to keep the center of pressure behind the center of mass, which helped maintain stability. However, fire arrows were notoriously inaccurate. Stability from the center of pressure only took effect once the rocket was moving, so while the arrow was still on the ground, it could lurch or fire in the wrong direction. The accuracy of fire arrows was later improved by mounting them in a trough aimed in the intended direction. The trough guided the rocket until it reached a speed at which its natural aerodynamic forces could maintain stability. However, the weight of the stick added dead mass to the rocket, limiting its range and performance. The rocket had to carry extra weight that did not contribute to thrust, which made it less efficient. A major improvement in rocketry came with the replacement of sticks by clusters of lightweight fins, mounted near the lower end of the rocket, close to the nozzle. These fins were made from lightweight, streamlined materials, giving rockets a dart-like shape. The large surface area of the fins helped to keep the center of pressure behind the center of mass, improving stability. Some experimenters even bent the tips of the fins in a pinwheel pattern to induce rapid spinning in flight. This spinning, like a rifled bullet or a football spiral, greatly enhanced stability. However, this design came with a trade-off. The added surface area of the fins increased drag, which in turn limited the rocket's range. Despite this, the use of fins became standard practice in early rocketry, marking a critical step toward modern, stable rockets. With the advent of modern rocketry in the 20th century, engineers sought ways to improve rocket stability while simultaneously reducing overall rocket weight. The solution came in the form of active control systems, which allow rockets to adjust their flight path dynamically rather than relying solely on fixed, passive devices like large fins. Active control systems include a variety of mechanisms such as vanes, movable fins, canards, gimbaled nozzles, vernier rockets, fuel injection systems, and attitude control rockets. Each of these devices plays a role in stabilizing the rocket and making precise adjustments to its trajectory during flight. Tilting fins and canards. Two of the most commonly used active control devices are tilting fins and canards. While these devices are very similar in appearance, the key difference lies in their location on the rocket. Canards are mounted at the front nose of the rocket, while tilting fins are located at the rear near the nozzle. During flight, these devices function like rudders on a ship, tilting to deflect airflow and cause the rocket to change direction. Motion sensors on the rocket detect unplanned deviations from the intended flight path, and small adjustments in the tilt of the fins or canards are made to correct the trajectory. The major advantage of these devices is that they are smaller, lighter, and produce less drag compared to the large fixed fins used in early rockets. This allows the rocket to maintain higher efficiency and longer range while still achieving precise control and stability. Vanes inside the exhaust. Some active control systems are designed to eliminate the need for fins or canards entirely. Instead of relying on airflow over external surfaces, these systems change the direction of the rocket's thrust to steer the vehicle during flight. By adjusting the angle at which exhaust gases leave the rocket engine, the rocket can alter its course with precision. One method for redirecting thrust is the use of vanes. These are small, fin-like devices placed directly inside the exhaust stream of the rocket engine. When the vanes are tilted, they deflect the exhaust gases. According to Newton's third law of motion, action and reaction, the rocket responds by pointing in the opposite direction. This technique allows rockets to be steered without adding external fins or canards, reducing weight and drag while maintaining effective control during flight. Gimbaled nozzles. Another effective method for controlling a rocket's flight is the use of a gimbaled nozzle. A gimbaled nozzle is designed to sway or pivot while exhaust gases are being expelled from the rocket engine. By tilting the nozzle in a particular direction, the thrust vector of the rocket is changed. In response, the rocket adjusts its course, steering precisely in the desired direction. This method provides an efficient and reliable way to maneuver rockets without relying on external fins or vanes. Vernier rockets. Vernier rockets are another method used to control a rocket's flight direction. These are small auxiliary rockets mounted on the outside of the main engine. When a course correction is needed, the vernier rockets are fired individually, producing a small thrust that causes the rocket to change direction. This method provides precise control over the rocket's attitude and complements other guidance systems such as gimbaled nozzles or vanes. Rocket control in space. Once a rocket leaves Earth's atmosphere, the methods used to control its flight change dramatically. In space, there is no air, so fins and canards are useless. They have nothing to push against. Any depiction of rockets using wings or fins in space in movies is purely fictional. In the vacuum of space, a rocket can only be stabilized or steered by either spinning it along the roll axis or by using active control systems that involve the engine exhaust. The most common type of active control used in space is the attitude control rocket system. Small clusters of engines are mounted around the rocket, allowing precise control over its orientation. By firing specific combinations of these small rockets, the vehicle can be rotated in any direction. Once the rocket is oriented properly, the main engines can be ignited, sending the vehicle in the desired trajectory. This method ensures precise maneuvering in the absence of air and is critical for orbital adjustments, docking, or interplanetary travel. Okay guys, now let's have a little quiz. The quiz consists of 5 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. What is the primary reason fins and canards do not work for controlling rockets in space. The correct answer is there is no air in space for them to deflect. Question 2. Which axis of rotation has the least effect on a rocket's flight path? The correct answer is roll axis. Question 3. Why must the center of pressure be located behind the center of mass for a rocket to be stable? The correct answer, it creates restoring torques that return the rocket to its flight path. Question 4. What is the main advantage of tilting fins and canards compared to large fixed fins? The correct answer is they are smaller, lighter, and produce less drag. Question 5. How do gimbaled nozzles control the direction of a rocket? The correct answer is by tilting the exhaust nozzle to redirect the thrust vector. Unlock the world of aerospace engineering with my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, you'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in the propulsion systems that power modern aircraft. Then, take your knowledge to new heights with Aerospace Engineering, Aerodynamics and Structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with Aerospace Engineering, Avionics and Aerospace Systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about forces and acceleration during liftoff phase. See you in the next video. Bye.